I think we are live. Uh, yeah, now I think we are live. I'm so bad at it. I don't know how to realize we are live or not. But yes, we are live, guys. We are live again. And the title today is That's a Rotate. Nice. So I will start with this video from C++ seasoning. Let me pause the music for a minute.
That's a rotate. That's a rotate. That's rotate. The rotate. Rotate. A rotate because rotate with rotate. Rotate, 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 and rotate, rotate, and rotate, 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 and a rotate. Rotate is a very common operation. That's a rotate.
Got it? So this is something that's a rotate, and we are going to try the rotate algorithm today, right? Okay, so what is the goal? I think I made a goals list. Goals, yes, this is the goal, and now it's not tomorrow goals, it's today goals. I need to figure out elements of programming implementation of rotate algorithm and Halo implementation of it. Maybe use GIMP for explanation. That is the first thing. The second thing I am interested in is, of course, implementing it in RSSTL. And the third one, that is a hard goal, but we can try that out, is implement the same algorithm in positionless design. The good thing is I have done a little bit of work, so I know that this rotate algorithm using positionless design is possible, or at least the way it is described it in cppreference.com. I think it's worth seeing one, right? So in the cppreference.com we have this sample rotate implementation, and this is a recursive implementation. For us, I think what we can target is, instead of doing recursive implementation, we can try tailcore recursion. That is another goal, I guess. And that's a detour. I do not know how interested I am in this tailcore recursion for RSSTL, because I have done this for positionless design, so I know it's possible, at least by using another parameter and a private function. So I'm not much interested in that, to be honest. So uh, let's leave that one. Hmm. But it's really nice to see how I did it in positions design. So if anyone would be interested, I can talk about it in some video, or maybe another live stream. Anyways, so I think I should open the elements of programming thing. Should I try some new wallpaper today, like this one or this one or this one, or even this one? This one I like, this one a lot, to be honest, because it gives a different feel and some anime kind of feel. It's fine. Hmm. But uh, let me first start with the what a rotate is. Hmm. I do not know what I did there and it crashed. So, anyways, regarding rotate, let's say I have an array with elements like 1, 2, 3, 4, 5, and I want to rotate this array after this position, right? So that means this position in the final permutation should come in the front of the array, and the elements prior to this position should come after the elements prior to these elements, right? So it should be like 4 5 and 1 2 3, and the algorithm should return us what is the next rotation point, like so what is the partition point basically, right? So that is something I want to do. hmm. I think I should open the elements of programming book so that I can figure out the rotate function. I think it's there in rearrangements algorithm, the rotate algorithms, right? So permutation P of n elements defined by an index permutation Pi is equal to I plus k mod n is called k rotation. That's nice. A permutation P of n elements defined by index permutation I equal to I plus k mod n, right? So every element is shifted by k positions forward. The inverse of k rotation of n elements is n minus k rotation, and that's fine. So an element with index I is in cycle I plus k mod n, I plus 2k mod n, and that is I plus mu k mod n. Hmm. Does that make sense? The element with index I is in cycle this. Okay. The length of the cycle is the smallest positive integer m such that equal to I plus mk mod n. And that totally makes sense, right? This all totally makes sense. This is equivalent to mk mod n equal to 0. Uh, is that the case? I mod n, that is I plus mk mod n. Which shows the length of cycle should be independent of I. Oh, that is an important observation. What it's saying that the length of cycle should be independent of I for a given k rotation. And that makes sense. If you think about it, that makes sense. Which shows the length of the cycle should be independent of I, since m is the smallest positive number system. Again, this makes sense. So the argument that mk mod n is 0 the LCM of k comma n should be mk. That is lowest common multiplier of k and n. And that is true because after that only, if it's not a multiplier of k comma n, the mod n cannot be 0, right? Wow. Where LCM of AB is lowest common multiple of A and B. That is so true. And then it goes the standard identity thing that LCM multiplied with GCD is the multiplication of those two numbers. So that is good observation. Wow. This guy just goes and says, what I'm thinking is this K would be a representation of position, and then now what he's trying to prove is how this rotation algorithm depends on GCD, and that is what Sean Parent said. Hello Amulya, how are you doing? Nice. So yeah, this is what Sean Parent said, that the simplest rotate algorithm is not just three reverses. It's based on this greatest common divisor thing, and yeah, that's nice. So and here he starts. Here he starts. K rotate from permutation random access. That's nice. So for anyone wondering why are we doing rotate, I can just stop the music. I can play that's a rotate thing again.
That's a rotate. That's a rotate. That's a rotate. That's rotate. The rotate. Rotate. A rotate because rotate, rotate, rotate with rotate. Rotate, 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 and rotate, rotate, and rotate, 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 and a rotate. Rotate is a very common operation. That's a rotate.
So that's a rotate, and we are trying to do rotate for RSSTL. That is my library. I am working for Rust Standard Library. I think I should have done the reading before coming to the stream, but yeah, that's fine. I can do it here itself. Hmm. Here we can see he goes with reverse bidirectional. That is the reverse algorithm, right? Three reverses. So that is nice. Rotate forward, annotated. Okay. Hmm. Wow, this is so hard to actually even understand this algorithm from elements of programming. I did not expect it to be so hard because we start with the mathematics, and that is what I expect from Stepano, right? Like he goes to the notion of the things, and mathematics is the notion of almost everything in programming. So yeah, I would go for Dave's implementation so that we can see this in code. I don't know if I have high-low. Yeah, I have high-low. Medieval collection.hilo. Ha. So P is the position where we have this partition point, and let's go. Let's see how we can do this. S is the start position, right? And E is the end position. M is P dot copy. So let's try to understand that. Hmm. So let me try that. I remember an example of A, B, C, D, E, F, G, H, I, J. I think that's a good enough elements for seeing the properties of this rotate algorithm. Now M is P dot copy. That means, let's say I want to rotate at this point. So M and we are right here. S is the start position and E is the end position. So yeah, that's nice. S and E, because it's the half open interval. Okay. If S is M, then return E, and M is E, return S. I think this makes sense because if middle is literally this, then we return E and we say that we transferred every element to the first partition, and it's vice versa, that M is literally E, then we say we return S and we say we transferred everything to the second partition, right? Because the second partition was empty, so now it should be full. So I am done with these cases. These cases are simple. What is the third one? The return point, that is E dot copy. Start with a known incorrect result. And that is something I do not like about this algorithm, that it starts with a known incorrect result. This thing does not fit good with my philosophy of positionless design, because the positionless design is actually very structural in nature, and we do not have this liberty of moving positions from one place to another like this, because we have structures around, and I have to figure out the structure for the whole thing. Anyways, so this thing I would call an R is also pointing to the end right now. That's fine. Now we start with the loop invariant. So what it does is exchange the leading elements of each region up to the shorter region. Nice. So what they do is they exchange the leading elements, and that is the swap. And here we can think about the GCD thing, right? Because we reduce the problem size by exchanging the shorter things like A and B, and then it becomes A comma B minus A. Where S1 is S dot copy and M1 is M dot copy. Okay, let me see. So this is S1 and this should be M1, and then we literally move forward and we do this swapping things. So that is nice. So for our case, it's literally we take 4 elements from here, 4 elements from here, and we swap it. So S1 should be pointing here, and M1 should be pointing here. Now, if M1 is E, then we have moved J elements into the position. If we have not, we can capture the return value, which is S1. Wow, is that true? So if we moved element J into the position, what is element J? Okay, that element J. So if M1 is E, that is so true, right? That means the second half is in the correct position, and we are quite done. Then what can be remaining there? I do not think anything should be remaining, right? Because this is what I want. I want Hij to be in front. Okay, but we have only moved ABC here, and now we quite want the rotation of this whole thing. We quite want the rotation of this whole thing. Nice. Okay. Wow, this is even exactly same as what I was thinking when I was implementing the start rotate given in CPP reference. And now the remaining thing, right? Okay, I need to hard time disable. I do not want hard time. Okay, so now I really want to rotate these two things, but S1 is the candidate where we know the result lies. I think we have done exactly the same thing. So S1 is right here and it should be right here. So what we can go is we have moved element J into the position. If we have not already, we can capture the return value, which is S1. If we have not already, so it's saying if return is E, then we do return to be S1 dot copy. If return is Z, that means we have found a return thing. Oh, nice. This is wow. So if anyone is wondering, this is something for which I introduced an additional argument for my optimization of tail call recursion. Wow. And then here this comment shows how Stepano was really concerned about efficiency, and he broke this thing into two loops, and that's fine. Hmm. If S1 is M, then we break. What does that mean? If S1 is M, then we break. Oh, so what was M? M was the point of rotation, right? So if I see in the figure, M was this thing, and I reached E. So if M1 is E, that means all the elements are moved, and if all the elements are moved, oh, we might be changing M somewhere. We have to exchange M. We are not. What? We are not doing that. Hmm, that is nice. But here it shows like M is a variable. S1 is M. Okay, yeah, here we are changing it. Here we are changing it. And that's the key. So we swap the initial elements, and now we have a smaller problem that is also a rotation. So we can adjust the bounds, adjust our bounds, and we can repeat. So that is S is wait, what? What? Wow. This is exactly same as. Oh, I need a git blame. This is Dave Abrahams, right? Yeah, because this is exactly same as what uh, the original implementation was for me. So if it's Dave, then only I can be sure. Now we have a smaller problem that is also rotation, so we can adjust the bounds and repeat. That is S is basically S1 dot copy, and M is basically M1 dot copy. My goodness, this is exactly the same thing. I did not expect. Like, what exactly is being happening is the same thing I am notionally doing in the positionless design. So this is not different at all. This is so not different. So we exchange the initial elements, and those initial elements are gone to done, and then we recurse, and then we do all the same things. Hmm. I think it's worthwhile to go and check it out how I did it in positionless Swift. Sources, positionless, algorithms, rotate. Hmm. So for rotation, in here for us is basically two partitions. We are given two partitions, and the second partition element should come before the first partition element. That is the rotation for us, right? And the partition boundary should be adjusted accordingly. Now we do this shift sections and transfer all to next and all those things, like, and then we call this rotate quarter section where the partition point matters. We call partition point matters. After that, it's a quarter section problem, so we rotate the quarter section, and if we see here, even if I remember it right, he might have done these base cases. Are good, but I'm thinking how this inner loop is actually handling these base cases, right? Because I have taken these base cases, handle the trivial cases. If S is M, then M is basically M1 dot copy. And if S is basically M, M is nothing but M1 dot copy. So if I see this whole thing, what I'm notionally doing is the second part and the fourth part, right? Uh, they are there for basically swapping elements around. So that is what we are doing, like swap first algorithm, and we swap first and third, and then we grow, and that is how we do swapping here, and that is the swapping thing. So this is a swap initial algorithm, right? This is a swap initial algorithm. We swap the initial things. Now after swapping the initial things, if part 1 is empty, That means the second case, we might have more elements. Left. This is so nice. So I think I should focus on the second case, and this time I would focus on like with this algorithm named swap initial in mind, so that I can actually think about it more. Right. There is any way I can go back, like mod P? No. Mod O? No, it's not there. Mod V, mod C, mod V, mod Z, mod X, mod N, mod M, mod this, mod A. I do not remember my awesome bindings, and now, okay, mod this, mod L, mod comma this, A. Okay, fine. We cannot go back right like that. I guess I should have put my GIMP on mod 1 so that I can just do 1 and 2 and I can just be happy, right? So let me take the second case, ABC to DEFGHIJ. Okay, A, B, C, D, E, F, G, H, I, and J. Now we are rotating, like we have partitioned like this, right? And then let's have a swap initial algorithm. So the swap initial algorithm, what it does is it swaps the initial elements. So it should be like D, E, F, A, B, C, G, H, I, J. Right. This is what the swap initial algorithm does. Now, for the swap, swap initial, what it should return. So one thing to return is clearly like this. But what is another thing to return? Another thing to return is the partition point on this point. But is it even useful? Is something I'm thinking. I do not think it's useful at all. The only thing I can figure out from this is if third partition has the second partition has more elements left, but why second partition is so important for us, right? So swap initials is by default swap initials is a quadri section problem. to get all the context. Is it what that mean? So what I'm saying here is that's what swap initially would return is basically A, B, C, this thing, not this one. It should be the other way around because we swapped right. So D, E, F, this thing, and A, B, C, this thing, and H, I, J. Right? And then we can be like, okay, if this partition is empty or not. Nice. Okay. But at any chance for our rotation, what we actually need is to know if Hij is empty, that last partition is empty or not. So my claim for swap initials is we need 4 partitions to actually do swapping the initial elements. And swap initial can return a true or false. So for true, we can say the first partition was empty, and the false we can say the second partition was empty. That is a nice property, right? So if we think like that, then part 3 had more elements. That needs to be the part of part 0. And we will swap initial. But we lose the context there. So ABC and Hij. Because if the second one is empty, we are quite sure, right? and ABC and HIG. Hmm. I lose the context of I have ABC. I am really hitting now hard time .nmem. This is just stopping my workflow. That's it, nothing else. Hard time and GCA this. I just cannot afford to interrupt my workflow at all. Now I need to check. So I do this swap initial thing, but I say I do not want to change the boundary, or is it good if we can change the boundary? What happens, like, let's say I have A, B, C, D and E. There are two cases like this or this. So if the case is like this and we say that we did a swap initial, it's DE like this, and it's A, B, E. So is it good enough for me? Like, is it very helpful?
Cambridge to Boston, lives in a world she's lost in, victim of compromise. He's staring at her Aberdeen heart.
I think having quarter section information throughout the algorithm is really nice. I think that's nice. Transfer over to next from to when. So I have two reasons from. So after this loop, we are quite sure that the third partition is empty. For sure, here we can say the third partition is empty. This is something we can derive. And then there comes, there will be some elements, and then we do this transfer to next because this is empty, and now we do this partition point matters thing. If partition point matters, we actually do recurse on a projection and we break. If partition point does not matter, that means I can just go inside this while loop, and this is exactly what is happening. The semantics are exactly the same, like it is not even different. It's not even different. So yeah, we are done with rotate. Now, nice. Uh, for RSSTL, I would like to have this rotate thing, but without recursion. Collection extension, a reorderable collection extension, and we need this rotate algorithm, right? So hmm, trivial cases. These two are trivial cases. Then we swap initials. So let's try swapping initials. Swap initials.
I'm far from home, no place to go, but I don't feel cold.
Swap initials
I've been so
till
blind, just
second
lost my mind.
partition is
But
empty,
all I have lost, I find your
right? So
face
we do swap initials till second partition is empty. This is what we are trying to do.
erase. I'll never be the same anymore. I'm on the highest stuff with no control. And you die. I open my eyes. Do you remember me? I can't
So
through all of these years you've been my
let
fantasy.
mute S1 is self dot start. Let mute S2 is self dot what's the next, like oh, this is S1, and I guess we would call it M1 is basically at, and now we, while S1 is not equal to E and M1 is not equal to self dot end, self dot end, oh, S1 is not equal to add, what we do is we basically swap the initials. This is what we do, we swap the initials. So for the swapping initials, we basically go right self dot swap at S1 and M1, and S1 is basically what does S1 is. So S1 is I need to think in terms of mutation. So self dot form next and S1, and same goes for M1. And because it's not Swift, we have real references in Rust, so I do need to pass them as reference. Now oh, EDR compliance. I don't know what is this EDR compliance thing. Nice. So now there are two possibilities, right? Um, one possibility is the first partition was shorter, and another possibility is the second partition was shorter. If the second partition was shorter, we are quite done. But if the first partition was shorter, then we are not done because we need to do more things. If I think it of what I want, if first partition was shorter, A, B, C, D, E, F, and the first partition was shorter, what I want is I swapped like CD and then AV and EF. But now what I want is EF should be swapped by AB. So if S1 is at, that means we are not quite done. What I want is so what do we want? If S1 is at, then I again want S1 to be so S1 is fine for me. Then what I want. So for sure, after the first pass, this should be at. I think even M1 is good for me. I want at equal to M1. This is something I want. That if S1 is at, now at is at M1 and again do this swapping thing. Right? Now we did that. The last thing I want is, let's say we did this initial swapping thing, then like that. So let me write it again. A, B, C, D, E, F, and that was the case. Now E, F is there, C, D is there, A, B is there, right? So one thing we know that I got the return point. This is the return point. One thing I'm sure that this is the return point. So I can just save the return point. If M1 is self.end, we are sure that we got the return point and we can just save the return point. So for saving the return point, we are like return is return. Return is basically S1. Okay, so S1 is the return point. Return is self dot end, and we got the return point here. Hmm. And as we get the return point, I again need to, but I need to break somewhere, right? I need to break somewhere, but I don't know where to break. What's the break condition? The break condition is surely we got as soon as the correct at the correct position.
Feel the power, now you're by my side. I've been searching, but you didn't hide. You were there all my darkest days. You look me in my eyes, and you feel like that
Hmm. EF should go to the front. That we did. And now we have the return point, but we have a sub problem to solve. This sub problem is just CD and AB. It's a problem to solve right now. It's again a rotate. It's a new rotate problem. But this time the return point does not matter to me. But there should be somewhere I need to break the loop. When we are quite done, we need to break the loop. So when S1 is at so M1 is self dot end. If return is not equal to self dot end,
can't break away. I've realized
right?
that I might just need to find another way.
And for now, I'm just doing the clones.
Instead, I need to let go. So just take it slow.
if return point is not self.end, we do return is s1.clone. I need to break this loop somewhere. But if we reach simultaneously, if s1 reaches at, if s1 reaches at, we are done. If s1 reaches at, we are done. So this is what we do. However, if m1 is the end, CD AB as soon as the right place, as soon as at the right place, when m1 is at the right place, just at is not at the right place. At
Wonder why, I wonder why I keep on trying to stay. Can't break away. I realize
if s1 is at is m1 not clone. Wow, I need. Can we? I have a new tab. Yes. A B C D E F. But now we'll do like this. So it's like C D A B E and F. So let me run the tests. I don't think tests would work at all. Yeah, they are not working. So
back on my feet, I fall right into you.
swap the
In the end, angel cries, oh what a wicked ruse.
swap the initial elements.
All of my senses, my heart screams the truth, and I can't help it. I walk straight to you. If love is my weakness,
Swap initials
I'll call straight to you.
and
No, I can't help it. My heart leads to
let's have some swap initial element sync, right? Fn swap initial. Hmm. Swap initials with I think this function is both of the parameters are as important, right? So fn swap initials, and I have c1, I have c2, and where c1 is a preorderable collection. Oh, you cannot swap. We cannot do that. Swap initial is not the thing because they are the same thing, and you cannot have two mutable slices. So that was possible there, but not here. Anyways, there you can do that in the positionless design. So we swap the initial elements of two partitions, right? So if first partition was shorter, then more elements of second partition needs to be in the first partition. So what we do is we just move at around okay, what we do is we move at forward, right? So if first partition was shorter, then we do this, but now we are like, okay, move. Okay, I need some more elements there. These elements are not good enough for me to think. A, B, C, D, E, F, G, H, I, and J. So if first partition was shorter, then it goes like D, E, F, A, B, C, G, H, I, and J, right? And now I'm claiming that let's move it like this and do something like D, E, F, G, H, I, A, B, C, and J, right? And then we again do move J here, and we do like A, B, C, A. Okay, and then at is at the right point. We just need to do the rotation again. So we move the elements forward to the first partition as far as we can, and this is what I was doing, right? So if S1 is at add, that means we are quite done, right? Now if uh, if second partition was shorter, so if second partition was shorter basically, then what happens? Control Y, that means A B C D E F G H I and J. We have things like this. We try to rotate and we reach this point where we have Hij and A B C D E F, not A B C D F G, it should be D E F G A B C. We actually got the point of rotation, so we return it, but now we just need to do the rotate. Now we just need to rotate, right? So what's the problem? So if seems so correct. Okay, so if second partition was shorter, then we get a new sub problem for rotation. So what is S1? S1 is exactly at the right place. I'm not getting why it is problematic. So if M1 is E, that is what I am thinking, and if return is okay, return is self dot end, then we do change return, right? And then if S1 is basically midpoint, then we break. This is exactly my intuition is. I'm not getting why. Okay. Now we do like this. If the first partition is shorter, then more elements second partition need to be in that. So it goes with S. Yes, S is literally S dot copy, and it was start. But not getting if S is M, then uh S is basically S1 dot copy. This is but why is S important at all? Well, S1 is out of it, right? So my claim is that we change S is to be S1 and then S1 is S. So do we use S here? No, we do not. We use S here, but that is S1. Just saying if S1 is M, if S1 is at, that was what I did, then at is M1 dot clone, and this is exactly what I write. I'm not understanding how is it wrong. Like this was my intuition. That was exactly my intuition. Wow. If S1 is at, swap initial of two partitions. If second partition was shorter, then we got if second partition was shorter, then we got the point of the point where if second partition was shorter, then we are done moving second partition elements, and thus we can conclude the return value if not already included. So if second partition was shorter, we're like M1 is self dot end, and if return is self dot, and that is what we do. If return is self dot end, we do not change E, right? E is not a var. Yes. If return is E, then return is basically S1 dot copy, and if both regions are of same size, You're done swapping, done moving the last element of second partition. We can okay, we can conclude the return value if not already concluded, right? And impossible return value, right? And if return value is self.end, return value is not found till now, return is basically s1, and if s1 is at both partitions were of same size, okay, and if now we have a smaller sub problem that is also a rotation, so we can adjust our bounds around feet. So if first partition was shorter than so in both cases we would have a sub problem or not. If we cannot get to M1, we say if S1 is at break, otherwise there would be more elements here. But now at any point what we can do is if S1 is at is I am not getting both partitions are of same size. If both partitions of are not of the same size, then we have a notation problem. S is S1 dot copy. S is S1 dot copy. The bad thing is it's literally S1, right? If S is S1 dot copy, that means if S1 is at and we do not change at here, we might be changing at somewhere, that is M. If while S1 is not at and M1 is not end, we swap, we do increment S1, we do increment M1. Now after doing that, if M1 is the end, we check if return is also end. If that's the case, return is S1 dot clone, and if S1 is at, that is M for us, break. The thing is, in the start of the loop, we need to make sure at M1 starts from at, and now we are done. Now we are done because we ensure that M1 always starts from at, and yeah, this is good enough. Because S1 starts from S1 always starts from S, but that was not the case in here. If S1 was not at, that means the first partition was bigger, M1 was last, and we need to move more things, and yeah, that's the algorithm. So the trivial cases are simply this, and then we start with S1, that is S, and M1, and then if S1 is not at, M1 is not that, return values, and if S1 is at, if first partition was shorter, then more elements of we got to if a smaller sub problem that is also a rotate. Yeah, we did a lot of things. Feed, implement non-recursive rotate algorithm. Yeah, that was all. We have finally implemented a non-recursive rotate for RSSTL, and that was the goal. I don't know what is the next goal for RSSTL. So what is next goal? The next goal for RSSTL is so we have rotate algorithm, and Now I think we should go for some more algorithms. One thing I want to think about positionless design, like what was that? Goals. So next stream. Okay. So goals. I want to see if I can project a bisection out of a quarter section. That is something really important. If I can project a bisection out of a quarter section, so for positionless design, because there are algorithms, the reasoning algorithms like rotate just work on bisection and not quadrisection. I see the cases where we might be working with quadrisection but may need to rotate, and thus this a good transformation. Nice. What is the second thing I want in positionless design? Second thing I think I want in positionless design is for sure mutable slices as an abstraction. Uh, should I open a new PR for that? I need to understand if we need mutable slices at all or not. Right. So that is a questionable thing. Like mutable slices should be an abstraction, and why we need mutable slices thing at all. The good thing is we have mutable bidirectional collection and mutable random access collection things. So now we know we can differentiate it and introduce it on the right places. Anyways, so yeah, let's start working on a positionless thing for the next stream, and rather than working on something on RSSTL, and then we can think about some algorithms like partition and partition point. I think I have partition point, but more and more algorithms, because at some point we have to introduce more and more algorithms before December, before Advent of Code. So that is the goal. So yeah, I think I earned stop the streaming here, and I did a lot. Thank you guys for the stream, and see you guys next time.